So what we talked a little bit about in class, expanding our division into how do we actually find zeros, roots, x-intercepts of polynomials. And how does synthetic division, or if you really want to do long division, feel free, how does that help us get this information? So if you look, and I kind of have already gone through the process because this is just a review, but if we take a polynomial and divide it by another polynomial, and we end up with this remainder of 0. So if you want to look through the steps, pause it, look through the steps, and realize, okay, everything's going to cancel out. We end up with a remainder of 0. The factor theorem said if you end up with a remainder of 0, x minus 3 is a factor. In other words, it tells us that 3 is a root for this polynomial. So what makes this equal to 0 is when x equals 3. 3 is going to be a root. So what we want to get to the point is now, looking at a polynomial, we can figure out, one, is a number a root or not? Is it going to be an x-intercept, a 0? And secondly, how can we get numbers that we actually can test, besides just being told, test if 3 is a root, test if 4 is a root. Instead of being told to test, we need to figure out how are we going to get these possible zeros. So first thing to realize when you're looking at a polynomial, so we start with x to the third minus 2x squared minus 11x plus 12, is a good thing to think about is how many roots do you expect. So the number of roots you expect is equal to the degree of the polynomial. So the number of roots, highest exponent, we expect 3 roots in this case. So it's always a good idea to know how many do you expect, and then so you know you're not testing 10 different numbers when you found 3. Now we come to what numbers do we actually test. So we talked about this briefly right at the end of class. And to test the roots, to figure out what we need to test, you think factors of the constant. The constant in this case, number at the end, constant, meaning no variables with it. Number by itself, so factors. In other words, what multiplies to be 12? 2 and 6, or 3 and 4. These are all factors. Anything that can divide 12 is a factor of 12. And then factors of the leading coefficient. In this case, there's no number in front of x cubed, so we assume it's a 1, so there's your leading coefficient. So factors of the 12 divided by factors of 1. So if we list out our factors of 12, we have 1, we make just a list here, 1 and 12, 2 and 6, 3 and 4, and that's all that divides 12. That's going to be the number we use for the numerator. In factors of the leading coefficient, 1 is just positive, or it's just 1. The thing about all these numbers is we have to consider both the positive and negative numbers. So this gives us a lot of possibilities. What you do is basically pick out any 2 numbers here that could represent your numerator and denominator. So you say positive 1 over positive or negative 1 divided by positive or negative 1. Well, that could be, so I could have plus or minus 1. Because I'm dividing by 1 here, so this is a division. You're taking any one of these numbers, choose any of the numerator, and choose it in any combination with the denominator, and our denominator is a little bit simple here, but that's how you choose your different possibilities. So in this case, we have 12 different possibilities for numbers it could be. Does that mean that we need to test and see to figure out which are roots that we need to test every single one of them? No, we're going to use we're not going to deny that we have technology here. We're going to narrow down the possibilities. So if we take a look at the graph, and we had a list of, I put all my possibilities out here, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. 12 different possibilities, and you look at the graph and you're going to narrow them down. We expect 3 roots. So you want to zoom your graph out enough to make sure you see, okay, there's 1 root, there's 2 roots, there's 3, to make sure you have all the roots accounted for. So I mean, if we're looking at our list, and we check out where it looks like the roots are, well, this left one looks at it's at negative 3, 0. This one in the middle looks like it's at 1, 0. And this one on the right looks like it's at 4, 0. Those are the numbers we want to target. We want to target the numbers that would be reasonable instead of testing all 12. Could you test all 12 if you didn't have the technology? Absolutely, but that would be kind of unreasonable. So how do we verify that these are the actual roots? That's what we're actually getting to. So besides identifying which roots we should be looking for, part of your job is to test our possible numbers. So test that these are the roots. And how do we test these? The idea is we're going to use that division. In this case, we're going to use synthetic division. Synthetic division, is it a root? It is a root if we're looking for a remainder of 0. So if each of those are roots, the factor theorem said they're factors, they're roots, they're zeros, if you divide and the remainder ends up being 0. So if we take each of our roots, let's take negative 3. And we do our synthetic division. And I'm just choosing the synthetic division because it generally views the easiest. Bring down the 1, multiply by negative 3, add vertically, so negative 5, and then again multiply by negative 3, multiply by negative 3 to get negative 12, and our remainder ends up being 0. So 3 is good, or sorry, negative 3 is good. It is a root. The nice thing, it's kind of a shortcut here. You think, okay, well now I tested negative 3, so now I need to start over the same whole process and just replace this with positive 1. Well, the nice thing is going to be that you actually don't have to start from scratch. Leave the negative 3 there. You can actually take your result here, 1, negative 5, and 4, and we can just continue along doing the same process with our next root. Because if it was a root of our original equation and we divided, or we factored it, your answers are still going to be a root of what's remaining. So if we do the same synthetic division process to 1, bring down the 1, multiply, add vertically, multiply, we end up with, again, a remainder of 0. So 1 looks like it's good as well. The graph didn't lie, but we're just verifying what we saw in the graph. And now we need to test our last root, 4. So do synthetic division on what's left. Bring down the 1, multiply, our remainder, so the problem gets easier and easier, our remainder again is 0. So this is how we verify, using that factor theorem, verify that you actually have roots. So coming up with the numbers and testing them isn't a difficult process, but it can get fairly involved if you get some fractions involved. And so when we're talking about possible roots, one thing we need to realize is that we're only talking about roots that are rational numbers. So rational meaning we could write them as a fraction. We're not interested in the roots that are like root 2 plus or minus root 2 over 3. We're not interested in the ones that we can get with the quadratic formula through this method. These are only going to give us the roots that can be written as fractions. So remember, so what are the possible roots? We need to think, okay, what is the factors of the constant over factors of the leading coefficient? So what can multiply to be 5? Well, in the numerator, we're going to have plus or minus 1, plus or minus 5. In the denominator, what can multiply to be 6? Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. So when we're picking what our possible roots could be, any combination of a number, pick a number, one of the 4 numbers we have listed in the numerator, pick one from the numerator and pick one from the denominator. That's how you make all of your possibilities. So if we listed out all the possibilities, that would take us quite a while, and that's why we want to look at this kind of as our guide, but then also realize, what does our graph show us? Well, it looks like and we expect 3 roots because of the degree. Looks like we have a root at -5, 0. So it would probably be a good idea to pick -5 from the numerator, +1 from the denominator, and test out -5. And we look at our other roots here. If I erase here, you can see more clearly. It's pretty clear that our graph dips down below the x-axis and actually crosses twice. There's 2 roots here, and it's really hard to tell what the numbers are, but they're definitely between 0 and 1. So what we want to do is pick numbers that are between 0 and 1 that are logical to test. What ones are logical to test? Well, look at our numerator, look at our denominator, and say, if I pick one in the numerator, and I pick one in the denominator, what numbers fall between 0 and 1? So what falls between 0 and 1? Well, if I pick 1 and 2, 1/2. If I pick 1 and 3, 1/3. If I pick 1 and 6, 1/6. If I pick 5/2, 5/3, 5/6, that's at least between 0 and 1. This gives us basically our list of what would we want to choose. So we know -5 looks like it's a sure bet. And then we got to figure out which of these 4 remaining ones make up our roots. So we're going to test to see which ones are our roots. So again, there's our list of possibilities based on the constant factors divided by the leading coefficient factors. So let's test the one we already know. -5. So remember, we're looking for a remainder of 0 to confirm that this is indeed a root. So bring down the 6, multiply. That would be -5. That would be +25 when you multiply. And then -5. So our remainder is 0. So -5 works. And now it's kind of a free choice. Whatever you think would be easiest to test, or whatever you think your best choice is, go for it. And we can actually do synthetic division with fractions. You just got to be more careful. So bring the 6 down. Times 1/2 would be 3. -5 plus 3 would be -2. Times 1/2 would be -1. And we struck upon, if we have a remainder of 0, we happen to have one number that is a root. So I picked 1/2. I made a good choice as far as what a root might be. The -5 is good, 1/2 is good because both had remainders of 0. Now let's say I tested 5/6. Oops, I guess I should put that a little higher. Bring down the 6. 5/6 times 6 is 5. Add down, and uh-oh, my remainder is 3. That tells me 5/6 is not a root. So if your your remainder ends up being not 0, that's a sign not a root. So we need to go back to this point where we had 6 and -2 as our coefficients and try something else. Let's try, I'll put an X, let's try 1/3. And you can use your graph to obviously make more educated guesses. If I bring down the 6, but I just wanted to show you what happens when you choose a root that doesn't work. Bring down the 6. Well, 6 times 1/3 is 2, and there's our remainder of 0. So 1/3, once you get to 3 roots that worked, you're good to go. So the roots for this particular equation, where it crosses the x-axis, -5, 1/2, and 1/3. So this is what we'll continue with. This is pretty much the end of section 3.